So, Dr. Steeves, I'd like you to come up here and do a little history for us here.
I feel in a way like I'm bringing coals to Newcastle, if you'll pardon the distorted metaphor, because here I am in Oakridge and from Madison, Wisconsin. We do have a nuclear engineering department there that I'm proud of, but I'm a retired radiation oncologist. And I did my training in radiation oncology at Albert Einstein College of Medicine, but before that I did a PhD in medical biophysics at the University of Toronto and an MD in London, Ontario. So I've kind of worked my way into radiation oncology and became interested in the environment and in climate change. And I've realized fairly quickly that the public has no clue about radiation, has terrible fear, and is being led down a garden path to think that 100% renewable energy is going to get us very far in terms of leaving coal in the ground and methane that I sometimes call devil's breath. And so it's the second last one. Leading a group called Pathways to a Sustainable Planet that's affiliated with the University in Madison, and we set up about 10 lecture series in the fall and 10 in the spring. And I've been doing this for 9 years now. And this past summer I was looking for something historical, and I came across this book as a result of this organization called The First Nuclear Era, and The Life and Times of a Technological Fixer. It is a great book. It's a sleeper. It's a 25-year-old book. I did not realize how delightfully written it is. Alvin Weinberg I've always admired ever since I first heard about him at this organization, but I didn't know how brilliant he was until I read this book, because you feel like you're passing along his neurons into the science, the engineering of nuclear energy, as well as his emotions, his moral feelings, and his delight in dealing with people and promoting molten salt reactors, which I completely agree with his impressions and feelings. So I found it a delight to read, and I'd like to share some of it with you. He lived about the same years that, well, he was born about the same time as my father. My father was an organic chemist from McGill who was involved in synthetic rubber and conventional explosives in the war. He told me when I was a kid, about 7 or so, that we were living in Kentucky at the time, he was working on synthetic rubber. He said, I've heard from a friend of mine who's working in Oakridge that there might be something to end the war sooner than we think. But he didn't believe him very much, so we moved to Lowell, Massachusetts. My father was working on proximity fuses, and suddenly Hiroshima happened, and we moved back to Canada. My parents are Canadian. But so it was a shock how quickly the war ended, but it had, although it saved many, many lives, it has left us with a dilemma of guilt, I think, to some degree, and that's addressed in Alvin's book. He talks about how the majority of people here at Oakridge voted to demonstrate but not actually explode the bomb on innocent civilians, and so that shows the morality of that. But of course, the president at the time was faced with a very different situation and responsibility and proceeded with it. But this is a wonderful demonstration of his early days. He came here with the Manhattan Project, supposedly to study beryllium and how it would be a good moderator for a chain reaction. And it was after his boss, Carl Eggert, left for California that Eugene Wigner came and informed him that the real purpose of his project was to create plutonium for use in atomic bombs. And both men worked out a theory of how the chain reaction can be achieved and the best way to study and analyze it. And so here's Eugene Wigner, a Nobel laureate and a brilliant man, and he worked very successfully with Alvin over the years. They had a number of other people here, well-known people in the field, Compton, Zillard, Zinn, Wally Zinn, who Alvin described as the most brilliant technical nuclear engineer he ever knew, and others here. Robert Oppenheimer visited occasionally. He was leading the project mostly from Los Alamos. Anyway, they had to ask and analyze, can we make a nuclear chain reaction? The interesting thing in the first paragraph is that there are limits. As soon as the first fission in a block of solid uranium takes place, the neutrons are slowed by collisions with the 238, the vast dominating element, and they're removed from the chain as they are converted into plutonium. So we need to maintain a chain reaction by doing three important things. First, we need to slow the neutrons to fission to a thermal energy level so that you can, as a moderator, get increased interaction with another uranium atom that's highly fissionable with a high probability. Secondly, you need to disperse the uranium atoms within the moderator. And he suggests we imagine that as uranium nuclei as raisins in a big cake of graphite moderator. And then finally, all these are going on the basis of an infinitely large pile. It's another name, of course, for reactor. But it has to be, it's not infinitely large, but it has to be large enough so that neutrons escaping from the surface of the pile are just balanced by those produced inside. And then the pile can become critical. So a lot of things have to be imagined here in this analysis of how to make a chain reaction. If the pile is larger than needed for criticality, then the reactor can be said to be supercritical. If it's smaller, subcritical, and if it's ideal, then you have a multiplication constant where K is equal to 1. And although to obtain a working pile, you really need to have it 3 to 4% above 1 because of the certain losses that will ensue. I found this drawing not too long ago and thought I would include it here. I think it's an interesting historical picture. We hear pictures of great surgeons having doing operations with medical students in attendance, and here is a group of 50 or so people who were invited by Fermi. It took him several years. He did 31 experiments all through 1942 and 1943 to refine the pile lattice. This required removing traces of boron from the graphite, as well as refining the whole pile lattice. The squash court was small in Chicago, and so only 50 people were invited. And since Wigner ranked, he was a junior guy at the time, just a recently graduated PhD postdoc kind of guy, and so he didn't get included, somewhat regretfully so. But that was a very exciting moment, and he described it in his book as one of the key moments in the development of man and his science. And I agree with that conclusion. So then he began working on designs for making plutonium that were efficient designs, and he and Wigner, mostly Wigner, chose water. A number of people wanted to use helium or CO2 under pressure, and various things were planned, but Wigner felt that water was the most efficient way to go. And Weinberg likened Wigner's creation of a complex reactor to Mozart's composition of a piano concerto. He said Wigner may have taken only 4 months, all of 4 months, compared to Mozart's few days, but the complexity was enormous. There are about 1,000 permutations and combinations. I think Wigner was very much influenced by fear of the day. There's a fascinating book just come out that I bought recently. It was a very prevalent fear that because of Lise Meitner and Otto Hahn's discovery of fission, that the Germans were working on the bomb. And so he viewed every day's delay for making the bomb as a gift to the Nazis, and that really drove him on. The concept of the breeder reactor is a fascinating one. Fermi and Leo Szilard were taking a walk, and one day, I think right in Chicago on the campus, and Szilard came up with the name breeders, and then they believed that breeders were essential back then. It's hard for us to imagine, but they thought that uranium reserves in the Belgian Congo were only a few thousand tons, didn't realize how much there was sitting around Western United States and Canada and Australia. And so they felt that it was really crucial to have a breeder. And as we began to find there was more uranium elsewhere, the need for having a breeder lessened, but Alvin had the insight to realize that there were some dangers in just using an open cycle, that we did need to have a closed cycle, and it's much easier to do that with a thorium molten salt reactor. And so he went around, and of course the lower temperature, lower neutron energy breeder is most feasible with thorium, and so he spent a lot of time advocating that. This is an interesting picture of the two of them, Wigner on the left and Weinberg on the right. They came along trying to find the most efficient way to advise the Hanford people into building reactors that would make more plutonium. And they came up with the idea that they weren't going to get very far by using non-enriched uranium. They really needed to enrich it more than the natural uranium have, and so where it's less than 1%, 235 isotopes. So they believe that it should be low enriched to something in the neighborhood of 3, 4, 5%, and that they wanted to use light water and pressurize it, and that would increase the efficiency, that they could consistently have a multiplication factor of greater than 1. As this was proceeding, Leo Szilard began to get worried that some of these papers on fission would get across to Germany and as they, or possibly Italy, as they proceeded, and he wanted to withhold these papers from publication. And then as he got thinking about it a little bit more, he heard of great progress in Los Alamos and began to worry about that there was a moral onus on us, not unlike that borne by the Germans who had first used poison gases in World War I. So he led attempts by scientists to mobilize against its use. Arthur Compton had to counter this with some specific choices and advice. There's a footnote at the bottom of that slide that might interest you. Alice Smith has written an interesting book called A Peril and a Hope, The Scientific Movement in America. I've not read the book, but I think it would make very interesting reading. This was the move to Oakridge here in May of 1945. It was called the Clinton, which was part of Compton's metallurgical lab. It was a sibling of his other branch at the Argonne, and it was run by DuPont and the Corps of Engineers. Its atmosphere, he said, was completely different from that of a university. And this photo shows the X10 research reactor built in only 9 months. Can you imagine building a reactor in only 9 months? I mean, it went critical on November 4th of 1943 and eventually developed 1 megawatt, just like a wind turbine of today. But of course, those were rapidly evolved. But none of these reactors were built primarily to make energy, but more for their ability to make plutonium. Alvin directed the Oakridge Lab. He was a director of research as early as 1948, but became director of the laboratory itself in 1955. So his presence here for a quarter of a century was, in a leading capacity, was very important. He said that not only were there 1,000 possible ways of combining various fuels and coolants, but I've underlined there or highlighted in yellow, once pressurized water gained a foothold, other possibilities were preempted as being too expensive. And that, I think, is a shame. Now, Rickover got involved. He was originally a student here, and later he became a captain, of course, to build the Nautilus, and wanted to use sodium, liquid sodium, and Alvin had to talk him out of it. And, but he did, and eventually, through one of Rickover's associates, managed to persuade him to use something that he felt would be safer. A number of crazy ideas happened in the early history of Oakridge. This nuclear energy for propulsion of aircraft idea came out, and the military literally demanded that this be built, even though, of course, it's hard for us to imagine that ICBMs were only a dream back then. But it was still wishful thinking because the smallest reactor would still weigh 50 tons, and shielding the crew would have added another 100 tons. Imagine getting all that in the air. And so that was eventually ruled out. But what Alvin saw, and Wigner too, is that aqueous homogeneous reactors, such as been described a few minutes ago, really had some major advantages. It could reduce complexity. Can you imagine all of the complexity of those assemblies that we have with the rods could be vastly reduced or eliminated. And he did describe in fascinating history the problem of xenon poisoning and how the accumulation of xenon as a fission product can seriously, it just soaks up the neutrons and seriously impedes the efficiency of the reactor. And they had to work on that. They started to build one out in Hanford and had some problems and called back, and everybody was in a tizzy about it until they discovered the difficulty that this fission product would have and how to remove that. There are some disadvantages, however, with these aqueous reactors. The entire circulating system, the pumps, heat exchangers, and so on become radioactive, so repairs manually can be difficult or at least hazardous to personnel. Also, to control the fuel inventory would be more difficult. If fuel precipitated in the system and segregated in one spot, there might be some overheating. So there are a few disadvantages, but some major advantages, and those were taken, those are now aqueous ones. If you took it a step further to a molten salt, that gave you some very significant advantages because of the thermodynamic stability of fluoride salts, allowing them to be inherently compatible with stainless steel pipes without using metal oxides and so on. These salts also boil at such high temperatures that they can operate at normal pressures, a wonderful advantage in sharp contrast with water, which needs 67 atmospheres. And of course, thorium came into the balance as well because it gave enhanced versatility so it could be used along with uranium. Thorium, of course, is a fertile atom rather than fissile as uranium, but with a little bit of uranium in it, it can generate the neutrons and go from there. So in this photograph, we have just a couple of things here. You can see at the bottom the holding tank and the freeze plug, a very handy way to provide terrific safety that we did not see in Fukushima, for example. That sort of thing could have solved that problem when they ran out of electricity. And also you see on the far left the reprocessing for getting rid of the gaseous xenon. This slide comes from a person well known to all of us here. Blocking on his name, moment, help me. Thank you. Pardon? What did you say? No? No, well, it might. I think I was thinking Canara, Alex Canara, I think. I got this slide from Canara. Okay. Anyway, I appreciate this slide. I'm not going to go through it in detail. We don't have a lot of time for that, but I admire that slide. I think it's a wonderful way to show the closed cycle of thorium. But the thorium thermal breeder was left to die in spite of Alvin's obsession with it and his trying extensively in 1958 and 59, traveling around the world giving optimistic lectures. But in spite of all, it never was pursued after about 1969 or so when that 3-year experiment was terminated. And he asked the question in his book, why? He said, well, first the fast breeder reactor was started, this one at Clinch River, a sodium reactor, and it was given preliminary support, eventually shut down because of cost overruns and some concerns over possible corruption of money used for its building. It was a really sad story when that closed, but when that closed, the thorium had already been second choice, and so it just never revived. On top of that, there was a fellow by the name of Milton Shaw, who was director of reactor development at the Atomic Energy Commission. He was not in favor of the thorium reactor and not a very good friend of Alvin's either. And so just looking back now at the history of light water reactors, I think this slide shows some interesting things. Shippingport, it's a fascinating story if you go back to read the wonderful book called Energy. on the history. It just came out recently by a guy, somebody's going to have to help me. Thank you. Richard Rhodes, thank you. Wonderful book in which he described in detail the shipping port, how Eisenhower got very upset that the Russians came out with the first peaceful reactor in 1954, and Eisenhower immediately called to get a reactor built in Shippingport in 2.5 years, and it was built. But the third time it was refueled. It was refueled with thorium and demonstrated very clearly its ability to be a breeder. So, but anyway, as these reactors began, you can see that the power increases. You can also see that in various years, the number of light water reactors in the United States were built. So the Europeans were kind of intrigued that we were building reactors even though we had a lot of fossil fuels around, and they didn't have nearly as many, so it also took off in Europe. But so there were 400 nuclear reactors by 1972, either operating or in construction. And then Alvin was the first person to talk about the Faustian bargain, that nuclear reactors create radioactivity on an enormous scale, and if a reactor failed catastrophically, radioactivity would be widely spread. This was an idea that Fermi had suggested back in 1944, and breeders produce materials that can be weaponized, and they were concerned about that too. I think Alvin, one of his mistakes was to have dinner one night with Ralph Nader. I don't know if any of you know that story. That was a suspicion. I certainly I agree with him, that was a mistake. He had some later critics, they thought he was a bit over-optimistic, but to his credit, and he was fired because of this, he says in 1973, I think he took nuclear energy and its safety importance too seriously for some people in power, and they thought that he shouldn't be leading it anymore, although they did recognize it, and he was eventually, after he left here, very, very active in energy think tanks, which he describes in detail in this book. It's just a wonderful summary. So we've got 5 minutes, so we'll wrap this up. He talks about the weapons connection, and he says that while a number of countries have built reactors, they didn't build a reactor first and then the bomb. If they were going to build a bomb, they went ahead and built the bomb, and even while this sequence doesn't prove that some country couldn't go the other way around, it's just such a difficult way to do it, and he wonders if we've not over-worried about this, and I tend to agree with him. Is it just a manufactured worry? There are no good examples of it yet, and I'm not sure that it'll ever happen. It's such a difficult way to make a bomb. Waste disposal is now a big issue, not only here, but in France, and there, of all places, they already have recycling in France, and yet the people of the Green Party in France is pushing the powers that be to cut back nuclear energy from their wonderful 78% that they have in France. Anyway, he asked the question near the end, could we have done better? And he had 4 ideas for the future, which I think are worth thinking about. He said, all reactors are now in relatively few sites, about 100 in this country. We have 80 acceptable sites now, so we just need 20 more, he feels, to do it. I think it's interesting that in many sites where there are plants, there are 4 or more reactors at those sites. And that's what he recommended, but in the United States here, we only have 1 or 2, occasionally sometimes 3, but the vast majority of sites where there are 4 or more are not in this country. We need to increase the security at these sites, professionalize the operators like we do airline pilots, to improve safety and properly recognize the quality and importance of our operators, and also to recognize the utility industry by separating nuclear generation of electricity from its distribution. And he mentions that the generation should be in the hands of a single powerful entity, possibly the government. We can see that a bit in the differences between France and the United States, where they have a more centralized government control, and I think fewer companies buying up utilities, buying up old companies and then sitting on the decommissioning funds and investing it for a little while. So it becomes an attractive buyout when you have devil's breath around. to put for your energy instead. He talks about key strengths pertaining to thorium. I've listed them here. I'm going to let you dig out of the book if you want, but there are some wonderful qualities of thorium. I've been criticized a little bit in Madison for conflating the advantages of thorium with those of the molten salt reactor. Yeah, the salt reactor is the technology, but there are reasons why thorium works very well in a salt reactor, and those are outlined here and very well in his book. So I'll wrap up the slide, my talk, with these last words of wisdom. He said, "During my life, I've witnessed extraordinary feats of human ingenuity. I believe that this struggling ingenuity will be equal to the task of creating the second nuclear era. My only regret is that I won't be here to witness its success." And he said that about 10 years before he passed on. This picture shows him, of course, with Kennedy as he visited. One last little slide here. He says, these are my words. I love this little cartoon. As we make the transition to thorium, and it's not happening as rapidly as we would like, we really need to rescue the plants we have. They're being bought up all too often. Diablo Canyon in California is one that's slated to come down in about 6 years or so. I think that would be a tragedy if that came down. We should be building them, not dismantling them. And so I have these old reactors, little sort of sad faces. They look kind of elderly. One's got a spectacle and they both got canes. And we do need to care for them. Michael Schellenberger, whom most of you must know, makes his whole career out of saving these. So thank you for listening and for inviting me.
Thank you, Doctor. Appreciate it.